Hello, my name is Lawanze Razor, and today I'll be presenting my model of the Cras protein, or Christian rat sarcoma viral oncogene homolog. This is what it looks like. It is a small GT-based protein that plays a crucial role in cell signaling. It is primarily located on the inner side of the cell membrane, where it acts as a molecular switch to regulate cell growth and differentiation. Mutations in Cras are strongly linked to various cancers such as pancreatic, colorectal, and lung cancer. Cras has a compact global shape with a cleft for binding GTP or GDP. To represent this model, I use pipe cleaners to show the structural connections, and these materials help illustrate the folding and flexibility of a Cras protein in a simple and yet effective way. Cras has multiple levels of structure. Its primary structure is the linear sequence of amino acids, which you can imagine as like the shiny sticks of the pipe cleaner. The secondary structure contains alpha helixes and beta sheets. The third level, or the tertiary structure, this is the fully folded 3D structure of Cras, and I use pipe cleaners to shape the entire protein. And the fourth degree is the quaternary structure, and Cras does not typically function as a multimer, so it does not have a quaternary structure, but it does interact with other proteins. Cras mutations are particularly at codon 12. I use the red pipe cleaners to represent the mutation in this protein. This mutation prevents the protein from properly hydrolyzing GTP, keeping it locked on its active state. This constant activation leads to uncontrolled cell division. Normally, Cras acts as a switch turning on and off, regulating cell signaling. However, when it is in its mutated state, it remains permanently active, and it is continuously signaling for cell growth and division. This overactive signaling contributes to tumor formations. This makes Cras mutation a target for cancer research and drug development. While my model illustrates how you can kind of picture a Cras protein in your head, it does not do its full justice because it has some limitations to it. One limitation is lack of anatomic detail. It does not show the exact atomic interactions that stabilizes the protein. The second limitation is static representation. Since Cras is a dynamic protein, which means it moves, this model obviously cannot depict that. And the third limitation is absence of cellular environment, so there's no like active cells around it to show how it interacts with other molecules. In summary, Cras is a vital signaling protein whose mutation can lead to cancer by promoting uncontrolled cellular growth. So this blue represents the overall structure of the backbone of the Cras. The green shows the functional regions, binding spots and loops, and the red highlights the mutation site as I previously stated.